Hello, everyone. Thank you very much, Frick, for that introduction. My name is Laila Bougria. I work for a company called Particular Software, where we make Service Bus. For those of you who don't know what that is, Service Bus is basically a messaging abstraction framework that allows you to focus on your business code without having to care how, for example, to get a message off a queue or things like that. So you can also find me on socials, Twitter or LinkedIn. Feel free to reach out. And that being said, I would like to thank the people from Full Stack for having me here today. It's an honor to be here. And then I would like to kick it off with a story. Once upon a time, there was a retail business that decided to build an online shop for their business. And as their business venture grew, so did the requirements and so did the system. Right? And they quickly understood that in order to keep up with all of the changing requirements, that they had to decouple the system. So slowly but surely, I can't walk too far away from this, so slowly but surely, they evolved the system into a true distributed system. And that also supported their idea of having their teams operate autonomously. And before you knew it, we had 3 teams in the house: Team Lorem, Ipsum, and Dolor. Dolor means pain in Latin, for those of you that don't know that. So as a way to communicate between those autonomous components, they chose to use messaging. So let's take a look at one of the most crucial business processes that's part of their applications, one that we can all relate to: placing an order. And we know the drill, right? We store an order, we want to charge the credit card so we can actually make some money. Then we want to package and ship the order. And then we also want to send the customer a bill. At that point, we also want to adjust the stock to reflect the sale that we just did. And we maybe want to figure out if we want to order some more stock to see if we're low on something. Finally, we also want to verify the customer status. It could be that that customer is now eligible for some kind of a discount code, or that they're now a gold customer because they've made 100 orders over the last month, right? If we look at these responsibilities in terms of the teams that manage them, then we can see that Team Lorem is responsible for that first bit of getting the actual physical order to the customer's house. Next up, we have Team Ipsum that's responsible for everything regarding the inventory. And we have Team Dolor that's responsible for everything surrounding customer care, hence the name. So if we start thinking about the system in terms of the messages that are flowing through it, then we could look at something like this. And there's a few components that might make sense. We have a sales component, finance component, and so on. The sales component is capable of processing a place order message, and it will also publish a order placed event at some point. But this doesn't really tell us anything about the system, because it hides away the entire complexity. Who's sending which message to who? How is the system interacting? How are these components coupled together, and who's reacting to what? In order to really understand that, we have to basically visualize things differently, and we have to think in terms of interactions between those components. And that brings us to a picture that's something like this. And this shows a lot more of what's going on. So everything starts with that place order message, and then everything just unfolds from that, and multiple components are reacting to multiple things that are happening. And we have decoupled the system by allowing some components to basically publish an event and have other components that are just responding to events that are happening in the system. And the advantage of doing things this way is that you end up with autonomous components. So autonomous components bring many advantages, and one of them is that it supports the idea of having their teams operate autonomously. And that means that they can choose whatever tools, programming languages, or frameworks that they feel most comfortable with or that are most applicable to the component that they are working in. It also means that each component should be able to operate in isolation, so that if one component is unavailable for some reason, that the rest of the system should be able to continue to operate. And as long as all of these components are interacting with each other based on a well-known contract, it doesn't really matter how they're doing things internally. That will also mean that they can also evolve independently. However, anything that can evolve independently can also fail independently. Let's take a look at an example of an error that Team Ipsum ran into. This is a call stack. It's a pretty simple example, just some pseudocode that I wrote, but as you can see at the bottom, we're basically handling an update product stock message. And when doing that, we're trying to get a product from a collection, and we cannot find it, so the product is not available. So looking at this, the engineers on Team Ipsum start running through a bunch of questions in their head. What happened? Where did it happen? In what context did it happen, and why? Right? Usually we'll look at the exception message to try to understand what's going on, and then see if there are any inner exceptions, look at the call stack, and usually from there on, we'll start debugging. Because debugging is a tool that we have available to step through things and build up the context of what's going on. What state do we have available? How are we changing that state? What type of parameters are we passing on to the next method? And that's how we can understand what the root cause of a failure is and how we build up that context. However, in a message-driven system, you're going to have to ask yourself a few more questions. First of all, you need to understand which actions started that change. So as we had in the previous example, the place order message that unfolds that entire picture that we saw. We also need to be able to understand which components were basically part of that entire chain, which components are involved in that business process. We also want to understand which exact flow of messages was being sent, because that could be different in different scenarios as well. And finally, we also want to be able to understand in which order did these messages arrive, in which order were they processed, and is there maybe a way that this could be affecting things. So let me step into the shoes of the engineer that's assigned this issue. And I will let you conclude if I'm drawing from experience right here or not. So I look at this example, I'm like, okay, seems like an easy enough issue. Let me just debug this. So I start up the component that fails, where the message fails to process, and immediately, boom, I run into the exception. At that point, I start looking at the exception, inner exception. I start scrolling through the call stack, only to scroll down and see, oh, at the bottom of that call stack, I'm actually ingesting a message from a queue. So I can't really see what got me here. Okay, I know. Let me just start the action that started all this, and then I should be able to debug through this and just F11 step into the next method, right? That should work. But that doesn't, because at some point I'm sending a message off to a queue that's being handled by another component. Okay, I know what to do. Let me just start the entire solution with all of the components in it, and then I should be able to debug through everything, right? That's not going to work, because we decided to split everything up in different solutions and even in different repositories. Okay, what I could do is basically start up 25 instances of my favorite IDE, connect the ones together that make sense, and then I should be able to do this, right? And it's possible, it's not impossible, but it's not going to be an easy job. Anyway, so I do that. I have 176 breakpoints set, and I'm debugging through the code, and I have this gut feeling that I'm so close to finding the problem. So I'm like, okay, F10, F11, I think I should be able to press F5 to the next breakpoint. So I hit F5, and everything seems to just pause for a second. And then I hit another breakpoint, and I'm like, dang it, the problem has already occurred. I forgot another breakpoint. At this point, if you know me at all, I'm already cursing in at least 3 different languages, and I need a little bit of breathing time. So I step outside, listen to the birds and the bees and do some breathing exercises, and I think to myself, what else could I do? Oh, I know. I could add some logging. Let's do that. So I go back, fresh energy, and I start adding log statements all over the place, trial and error mode. And I'm debugging through things, and I'm looking at these log statements, and I see, Okay, I'm here. Okay, this output, order 125. Wait a second. Wasn't I just debugging order 326? So I look around at my colleagues and I'm like, is there anyone else creating orders on the test environment right now? Because I'm debugging something. Is this message even mine? As you can see, a whole lot of frustration, and I still haven't found the problem, right? So the rest of my coworkers look at me and they're like, Laila, what are you doing? Are you debugging this? And I'm like, And they say, do you think anyone at Amazon runs into a failure and thinks to themselves, oh, let me just debug through this? Well, when you put it like that. So, what do we do instead? Well, we test. And if I'm stating the obvious to you right now, then more power to you. But I think we don't sufficiently stress this enough, especially in large distributed systems. Because whether you test or not should be completely independent of any architectural style that you are using. But if there are many components involved, then it's a necessity at that point, okay? So there are many forms of testing available, completely out of scope of this talk. I'm sure you've heard about them, and they're widely documented. So if you're not doing that sufficiently, then it's something definitely to consider. If you run into a failure, add a test. You're probably missing one test. Well, you are missing one test, but probably more, okay? And I'm not going to go too deep into this topic, but I want to give you one pointer, because one of the things that we want to do is rethink the AAA syntax. Who has heard of that before? Okay, so the AAA syntax is basically a way to arrange your tests, and it basically, the AAA stands for arrange, act, assert, right? So in the arrange phase, we usually prepare our input. In this case, that's going to be a message. In the act phase, we're going to invoke the message handler that would then process that message, still pretty much as a normal AAA syntax works. And then finally, it's the assert phase, and that's where things get interesting. Because not only do we want to verify all of the desired outcome in terms of state changes, API calls, and whatnot, but we also want to verify all of the messages that we are sending out as part of that processing. Because we also want to check every property of the message that we are sending out, because that's how we can ensure that we're doing a proper handoff to the next component, okay? So, okay, we say, we're going to do this testing thing and we're going to do it consistently. We have a lot of trust in our system, and at some point we decide we're ready for production. So we just deploy it, and it's been running in production for a while. Everything is going well. And then there's this guy, Murphy, that comes knocking on your door, and there's a failure that occurs in production. So what do? Easy, right? I just told you that whenever you run into a failure, you're going to add a test. But what if you look at that message that just failed, and you look at that input, and you say, well, this information doesn't even make any sense. This isn't a scenario that should even work. Let's take a look at an example. So the call stack that we looked at earlier, we were trying to process an update stock message, right? And that ran into an invalid operation exception because the product does not exist. We could not find it. But we're just being passed the information there. The ID is wrong. Where did that come from? So we have to move up the tree to see who sent us this message. That would lead us to the order packaged event. But that's not doing anything else except for reaching over the order lines and just passing that information that's there. So we have to move up one more step in the tree, which brings us to the order placed event. And there we can figure out, we didn't correctly map those IDs, and we weren't passing anything that makes sense, okay? But how do we solve this problem when there are so many components involved that may even not be managed by our own team? And the thing is that we can't really focus on just a single small part to solve these types of problems. We have to be able to look at the big picture. And we want to be able to follow a transaction through all of the participating components of that system to understand where things might be going wrong. We want to look at each step, and each step should also have some context associated with that so that we can understand, okay, what type of data was it working with and what was it passing on? And that's exactly what distributed tracing is for. And distributed tracing is quite the hot topic today with the rise of microservices. However, it's not really new at all. It goes back to the beginning of the century when service-oriented architecture was the hot topic of the day. But it doesn't really matter what type of architectural style that you are using in your system, because once you start decoupling things and you have multiple components, you need to have a way to basically understand how a transaction is traversing all of those components to get to the root cause of problems. So, okay, our team say, you know, we are done with this pain. Let's implement distributed tracing. And they start looking at what's available, and they see that there are actually many frameworks and tools available to do this. And, you know, our teams are autonomous, right? So we have Team Lorem that says, oh, we're going to go with Datadog. And we have Team Ipsum that says, yeah, well, we really like Jaeger. And they hit another wall. Because although the traces that they are collecting are super, you know, interesting and they're an added value to the system, they are stored in a vendor-specific format. And basically, you can look at, you know, the small part of information and it makes sense, but you're still unable to bring everything together at that point. And it's problems like these that led to a higher need for standardization. And what happens? Standards start popping out of the ground like mushrooms. So then we had open tracing by the CNCF. Around the same time, we had Google that open-sourced open census. And the vendor started saying, you know, how many standards do you want us to support? Can't you just please, you know, get into a room and agree on one thing? And that's exactly how OpenTelemetry was born. So what exactly is OpenTelemetry? OpenTelemetry is basically a collection of tools, APIs, and SDKs that allow you to instrument, generate, and collect telemetry information about how your system is behaving. It allows you to analyze and understand the behavior from outside of your system. And it's available in multiple languages and platforms, and I'll get into that a little bit later. And what's really interesting is that it's completely independent of any underlying stack that you are using. So you can still bring all of that information together. So I'm mentioning it's cross-platform, cross-runtime. And I'm mentioning observability framework. But what is observability exactly? Well, for software to be observable, you need to be able to understand how it works internally without making any changes to the system. And not only do you have to understand how it works in expected states, you also have to figure out what is going wrong when things are not working well. So you basically have to know what you don't know. And to make things worse, you can't make any changes to your system and deploy new versions when doing that. And you have to be able to understand this using external tools. And usually that information is also stored outside of the system. So if we look at OpenTelemetry, it actually supports multiple observability signals. We have traces, logs, and metrics. And what's important here is that OpenTelemetry is not the same as distributed tracing. Distributed tracing is just part of the OpenTelemetry offering. Okay, there are also logs and metrics available, and metrics allow you to sort of see, something may be wrong over there. And then the traces allow you to go deeper into that and to see, okay, what's actually failing here. Logs, I hope we're all familiar with at this point. It's something we've been very widely using in our systems for years. But all of these things combined allow us to really understand what's happening in our systems from the outside. So let's start with traces. What exactly is a trace? Well, a trace basically tracks the progression of a request across multiple boundaries. Think process boundaries, network boundaries, even security boundaries, right? Any subsystem that you may be using, whether that's a database, some kind of a blob storage, or a message broker, you can basically see how that transaction is touching all of those subsystems. It basically represents a tree of spans. So what's a span? A span is basically a single unit of work that is part of that trace, and it represents one tiny step of that entire transaction. It could be getting a message from the queue, for example. So that's a little bit abstract. So let's take a look at an example. I drew this myself in PowerPoint. It took me a lot of sweat and tears to do this. So it's not a screenshot from a tool or anything, but it's a visual representation of a trace. As you can see on the left bar, all of it is a single trace, and it starts in an API when we call order/create. Then we're sending messages, and multiple components are interacting. As you can see, the colors change. When we, for example, publish an event, you can also see there that there are multiple components that are reacting to that same event and are processing that. That looks pretty familiar, actually. It's basically a distributed call stack. And it gets even better, because you can basically take a magnifying glass and look at a specific span and get additional information of what's happening there. You can see, oh, that charge order message, oh, it was actually a message with that ID. And it was being sent to the finance queue. And it's a send, so it's not a publish, so you get additional information. You can also add things, like, for example, I have information about the order available. And what's also cool is that it also tracks the duration that it took for that specific span to complete. So you also have that information. If we bring it back to the example that we were trying to solve earlier, then let's see how we could do that. What we would do is first see, okay, there's something actually failed, right? An exception was thrown. So we can look for the traces that failed. And that would show us that the update product stock spans there are failed. Then we would go up the tree and try to understand, okay, where did things go wrong, which would lead us to the order placed event that's being published there. And if we look at that context, we can see, oh, look at that. We were passing in the order ID to the product ID, so things weren't correctly mapped, right? So how do these things get connected? Well, for a trace to be distributed and therefore available across multiple components, it needs to have a propagation mechanism, and that usually occurs through a standardized protocol. And one of the protocols that's recognized by the OpenTelemetry specification is the W3C trace context for HTTP headers. I always feel like I need to take a deep breath before I say that. It's so horribly long. But basically, the only thing it does is add a header to every outgoing request that is called a trace parent, and it looks something like that on the screen, which looks like a few IDs basically glued together, and it's exactly what it is. Because that first part represents the version of the protocol, which in this case is 0. And the next part represents the trace ID. And that's what we are going to propagate to every call down the line, right? So that's going to be assigned once and then propagated to every other call that's part of that transaction. The next part is a span ID, and that's going to be unique for every unit of work. At the end, there's also some trace flags available so that we can see if that trace was being recorded or not. So if you think this is actually a good idea and this could help me and you want to get started with it, it's actually really easy to just get started. Because the only thing that you need to do is figure out what type of information do I want to collect. So you can select sources from which you want to collect telemetry from, and then you're going to set up an exporter, which is where you want to send your data to, and that's going to be visible then with whatever tool you use. And that's it, really. And here at Full Stack Europe, we're full stack. So I also want to underline, because I'm a C# developer, in case I forgot to say that, but I also want to underline that OpenTelemetry has been implemented in many different languages. So if you can see if you can see the language that you're mostly using, odds are that it's going to be in that list. It's really widely been incorporated. As the examples that I'm going to show later are going to be in .NET, just because it's what's most comfortable to me. If we think about the exporters and tools, there's many options available, and these are not all of them. There's just, tools are being added to this list every day. It's hard to keep up. But the beauty of a standard is that it doesn't really matter, right? It doesn't really matter which tool that you're going to use. So if you're already using one of them, then just use that. Or investigate all of them and see what you like best. Once you think, okay, I can already think of so many scenarios where I want to add tracing in my application, then I'm going to tell you to pause. Because before you do that, you need to look at all of the libraries that you're already using today and see if they have support for OpenTelemetry. Because this is the .NET stack, but as you can see, there are plenty of libraries that already support OpenTelemetry today. And there's no need to go reinvent the wheel. So collect that information, look at it, see what's useful for you, and then add to that, enhance that further. Before we actually add some traces, there's a few questions that you need to keep in the back of your mind when you're adding traces to your application. First of all, can you easily connect the user action to a trace? Why is this important? How many issues do we get in our inbox that we try to reproduce and we're like, I can't reproduce this, it works on my machine. Well, great. Can you then ship them your machine? Because that user actually did experience some friction at some point, right? But if you're able to connect the user action to a trace, then you could actually go look at the information and figure out in what context they were running, what were they doing, and see what exception they ran into, and how is the system behaving at that point. Another thing you want to remember is when I'm adding telemetry is, can I easily group similar traces together? Because you'd like to be able to figure out if there are things that stand out in performance or in duration, and why that is. What is there special about those specific traces? What are the most load-generating parts of your system? Is it maybe specific to a user segment, a location in the world? Could it be when there's a specific subsystem that's being accessed that you can see the system struggling? Those are things that you want to be able to identify from the traces that you are collecting. You also want to be able to understand which users are stressing the system. What are they doing? In what order are they doing it? And another thing to keep in mind is how will you, in retrospect, be able to easily find suspicious events? So let's say, for example, that there was a bug in the system, right? And you want to be able to understand how many users that affected. That's something that you could or should be able to extract from the tracing information. So now that you know everything you have to think about, let's take a look at actual code. So this is C#. I'm going to assume everyone can follow along, but I'll explain. So the language is a little bit different in .NET. I have a source there that actually represents a tracer, and an activity is a trace. An activity is a span. So the source is actually the tracer that's going to collect an entire trace. Okay? So I'm creating an activity there. It's nullable. And why is that? It's basically a performance optimization. Because if there's no one collecting that information from that source, I'm going to get a null back, just to avoid additional object allocation for nothing. I'm also using a using statement. That sentence is hard to say. Why am I doing that? Because the activity will be stopped for me when the object is disposed, and I don't have to care about it. We're also going to add tags. Now, what is important about the tags, or rather, what do you want to add to tags? When you are working on a piece of code, ask yourself, if I were debugging this right now, if I was trying to find the bug in this piece of code, what variables would I be looking at? What state is important right here? What am I touching? What could be of essence for this specific method? And those are the things that you want to add as tags. It's basically a key value dictionary. You can also add events, which is like a very minimal type of logging, but more about that later. And finally, you can also see that I'm catching any exception that might occur, just so that I can set additional tags. Those are going to signal that those traces failed, so that I can easily find them in the tool that I am using. So if you look at this, it's like, okay, but you have that stock recalculation starting and stock recalculation completed. It looks pretty similar to logs. Should we then just stop logging altogether and just throw away everything? Well, not really. Instead, what we want to do is keep the traces high level and focused on what variables are floating around and what type of state changes are we making. And we want to then log all the details. You can make that as verbose as you want, but that's not something that you want as part of your traces. What is crucial, though, is that you want to connect the traces and logs together. Because if you then go look and there's something going on, then you want to be able to see, okay, if you see something that's off in the logs, for example, and the log statement contains the trace ID, then you could take that and go to your tracing information and see, okay, what was actually going on here, right? We've also been logging in our systems for a lot of time, so getting rid of the logging would be a little bit crazy. Let's try to reuse what we have and enhance that. To the previous point, if you are in the .NET stack, I have a sample available on how to do exactly that, which I'll be sharing in the resources at the end. So, apart from investigating failures, because that's the main benefit that I have spent the last almost half an hour talking about, there are plenty of other benefits that you get when you increase the observability in your system. One of them is the ability to perform postmortems. And I know that sounds awful for a Friday afternoon, right? But think about it. Let's say there was a Black Friday. And all in all, everything, was okay. Nothing, the system didn't crash. We were able to actually sell a lot of products. But having the ability to then go back and see where was the system struggling? At which point did the system take longer in actually processing orders or even accepting orders? Having the ability to then go back in time and see, okay, what did my infrastructure look like? I mean, we love auto-scaling these days. What did my infrastructure look like when I was seeing this type of load? That's a really powerful thing. Another benefit that we get is a better way to deal with feature flags. So especially in large systems, sometimes we introduce a new feature and we say, we're not going to roll this out for everyone. We're just going to roll this out to a specific segment of our user base. And we could even be doing that for multiple features at the same time. But if then a user runs into a failure, we need to understand what features were enabled, even which specific combination, because that might also be causing some side effects that we may be unaware of. Another benefit that we get is around chaos engineering. So it's another hot topic right now, especially with services like, Azure Chaos or Chaos Monkey, for example. These are services that are just that allow you to basically unleash chaos on your system and see where it starts failing. But if you then have to figure out what went wrong without any observability in the system, then good luck. I'm out. So as you can see, we get a lot more when we start increasing the observability in our systems. And that brings me to the recap. I hope I have convinced you all that observability in your systems is crucial. And most of us already knew this because we were doing a lot of logging, but there are ways to meaningfully expand on that. Investigate OpenTelemetry that's being emitted by the frameworks that you're already using today, okay? So there's no need to immediately say, okay, I need 6 weeks now because I'm going to implement OpenTelemetry in the application. Just start small, look at what's already being emitted, set up an exporter, look at that information and see what you can learn from it. What you do want to immediately do is connect that information to your logs so that you can basically create a better view of what's going on. And finally, you can just take a step-by-step approach to this. So you can enhance and enrich the information you have. If you see, okay, this is a blind spot in my application, then you can start adding tracing there. Okay, that was about it. I hope this was useful to you. If you have any questions, feel free to come find me. You can also always contact me on LinkedIn, Twitter. You can find me on GitHub as well. And if you follow the QR code, it leads to one of my GitHub repositories where I have additional resources available around the topic. I also have some samples available, for example, how to connect your traces and your logs. I also have some examples within Service Bus, so be sure to check that out. Thanks a lot for listening.
Thanks, Laila, for another excellent talk. Right now, we have a break, and we'll be back at 4 o'clock with the final round of talks. See you after the break.